In this video, we're going to take a look at a bit more background information before we jump into our Bohr-Rutherford diagram or our Bohr model of the atom. So let's go take a look at Planck's idea of quantization and then the famous experiment that Einstein did using the idea of quantized energy. So classical physics had the idea that energy is continuous or was continuous. Essentially, if you released energy from, let's say, for example, a toaster or a microwave, energy would be released continuously and would just continue increasing and increasing and increasing to the point where making toast would basically destroy your whole home. But that wasn't really happening. So this is classical physics. You're basically increasing the amount of energy continuously as you're releasing energy from a source, and that wasn't happening. Instead, what was happening is that there was sort of a level off that was happening at different temperatures. So energy couldn't have been released continuously like classical physics was saying, like this here. There must be some level off and drop. So Planck suggested that rather than energy being continuous, energy exists in packets. It's quantized. Think of it almost like money. Money exists in nickels, dimes, quarters, loonies, toonies, $5 bill, $10 bill, so on and so forth. It's not a continuous range in between all those values. If you have that money you're trying to exchange for something, it exists in those quantized values. And so those are packets of money, just like there's packets of energy. That's what Planck was saying. And so a packet of energy became known as a quantum, or plural is quanta, with an A instead of UM. So rather than think of energy as being continuous, like in the classical sense, energy now became little packets of energy instead, almost like packets of money. And that helped to explain why, when you're using your microwave or your toaster, you're not getting this continuous release and increase of energy throughout. Instead, you're seeing more of this trend here, or this trend here, or this trend here, depending on the temperature you're at, for example. And it worked. So it's a simplification, but the main idea I need you to get is that energy is quantized, exists in little packets called quantum or quanta plural. So think of classical physics thought energy was continuous, like this pole, sliding down a pole. There's all these values in between that exist for energy, and it continues existing like that. Whereas now quantum physics, the more modern physics that we see today, has energy existing in steps. There's a step here, a step there, a step there, and a step there, and you're using only those specific steps for energy. So energy is quantized in little steps as opposed to continuous at this point. Now, let's take a look at how Einstein used this idea to explain a really cool effect called the photoelectric effect. Einstein did an experiment with sheets of metal. So let's say there's potassium metal here. Einstein shines some light onto the sheets of metal, and he wants to see which light would knock electrons off of it. So when he would shine red light onto it, no electrons would jump off. But if he shines some green light onto it, then electrons would come off the sheet of metal. And that's the photoelectric effect, where you shine light onto a piece of metal and electrons jump off, but not all colors of light did that. So Einstein had to explain why that was. Einstein thought, well, you know what? Planck said that energy can be quantized. So why can't I think of light that way as well? Light's a wave, a continuous wave, but why can't the light also be quantized in little packets? So Einstein basically said that light can exist as both a wave and a particle. It exists as a wave, but you can also think of it like a little packet of energy as well. When you think of it as a packet of energy, you call it a photon. And that's the wave-particle duality. Light is both a wave and a particle, and the energy within the light exists as photons, which are basically just quanta of light, a quantum of light energy. So light energy exists in packets. The name for a packet of light energy is photon. And Einstein kind of got that idea from Planck's idea of energy is quantized. So how does that explain the photoelectric effect? Well, what he's saying is it didn't matter how much red light he put onto this potassium, no electrons ever came off. What that basically means is that the packets of energy in the red light were just never enough to trigger the electron to be removed. So you could shine it on all day and as much as you want, but it won't move it. But the packets of energy inside the green light were enough to move the electron, where the packets of energy in front of the blue light were enough to remove the electron. So you can kind of think of it like if there's a chocolate bar for $2 and you only have a loonie. It doesn't matter how long you hold that loonie up to the cashier. the cashier will say, well, you can't buy the chocolate bar. Your packet of money doesn't have enough energy in there. There's not enough money to buy this $2 chocolate bar. But as soon as you present the toonie, then you've met the amount of money you need and you can buy the chocolate bar. So this is like the loonie, and the electron needs $2 to be removed, $2 to be removed. So the loonie won't have enough no matter how long you hold it up for. But the toonie will, and that's the green light, for example. And that removes the electron. So now we have energy that's quantized from Planck. And Einstein's saying, okay, now our photons are light. Yes, it was a continuous wave, but it could also be a quantized particle, a photon. So the energy in light's also quantized. Another way to think about this analogy is if you have a bowl with a marble in it and you have it on the table and you want to hit the table so the marble jumps out. If you don't hit the table hard enough, the marble jumps a bit, but just stays in the bowl. Doesn't matter how many light taps you do to the table, the marble will just kind of jump within the bowl but stay there. You can do 1,000 of those light taps and the marble still stays there. But all it takes is the right hard tap, the right packet of hard tap, one hard tap, and the marble can actually jump out. So you can do a little bit, light taps, light taps, light taps, and the marble won't jump out. Light taps from the red photon, the marble won't jump out. But you have enough energy in this packet of UV, and the marble does jump out. So light energy can be thought of as existing in little packets. Red has a small packet of energy, yellow a little bit larger, blue larger, and UV even larger, for example. So packets of light energy exist, and they're called photons. So that's where we get into the idea of Bohr's model. Bohr had to solve a problem. The electron is always moving around in the nuclear model from Rutherford, and so it should lose energy continuously and collide into the nucleus and then obliterate and just be destroyed. But Bohr said, let me take ideas from Planck and from Einstein and put them into a new model, because our model should also follow the law of modern physics, not classical physics with continuous energy. So Bohr said electrons exist with their energy at quantized steps. So their energy is also quantized. That's where he said that some electrons can be at energy level 1, some electrons at energy level 2, some electrons at energy level 3, 4, 5, so on and so forth. So now the electrons are no longer just kind of orbiting and losing energy continuously. They're found at specific quantized energy level. And those specific quantized energy levels are defined, like having a loonie, a toonie, and then a $5 bill, for example. And that's what leads to our Bohr model. Bohr took those ideas and said, let's get the energy of electrons quantized as well. And that helps to solve the problem of the electrons continuously losing energy so they don't collapse into the nucleus, sort of. So this was the classical physics sense. The energy in electrons is continuous and it's like a ramp. But now with Bohr's model in a quantized model, also called planetary model, the energy exists in little steps like this. So a step of energy over here, and over here as well. And that's where those electrons will exist. So these are the main points, according to Bohr, that electrons will exist in orbits, kind of like the planets orbit around the sun. And they're basically held in those orbits by electrostatic forces from the positive nucleus. And the electrons can only exist at certain orbits. Only certain orbits are allowed. So one here, and one over here. And there's a different amount of energy in each. Usually there's less energy when you're closer to the nucleus and more energy when you're farther away from the nucleus. But either way, what this means is that the energy in electrons has now become quantized as opposed to continuous. So nice little steps. While the electron is in its orbit, it's not losing energy. And Bohr couldn't really explain why that was 100% yet, but while it's in orbit, it's not losing energy. But electrons could jump from one orbit to another. So if you give them energy, they could jump up. But then when they're up, they also want to come back down, so they release that energy that they absorbed. So if you give an electron a photon, meaning energy in the form of light, the electron will absorb it and transition up to a higher energy state. But then it goes back down to the lower energy state by releasing the energy as well. The lower energy state, when it's closer to the nucleus, its default energy state is called the ground state. And when it absorbs light and jumps up, that's called the excited state. So ground state, absorb energy, excited state. Release energy, and you're back down to the ground state. And as you're probably connecting now, Bohr started to connect. Bohr was able to use his model to explain these atomic spectra. That's what was really neat about Bohr's model. He could explain the emission spectrum for hydrogen. Where did these lines come from when you heated up something like hydrogen or gave it electricity? Why were there lines? Well, that came from electrons jumping up and then going back down. And when they went back down, they released energy. And that released energy is what you see as these different lines here. So let's go to this slide here. This is our hydrogen atom. This is a continuous spectrum. This is the emission spectrum for hydrogen. This line here can be attributed to the jump from energy level 6 to energy level 2. It makes sense. It's the biggest jump and it's the most energy. It's the smallest wavelength. This line here, for example, can be attributed to energy level 3 to energy level 2. It's the longest wavelength, so the lowest energy. It's the smallest jump. But Bohr was able to confidently and accurately predict and explain the atomic spectrum for hydrogen using this idea of quantized energy level. He could explain where all of these different emission lines came from, which was a great part of his model. And so again, how does this work? Well, the electrons absorb energy in the ground state to become excited, and then they release the energy to jump back down, and the released energy is captured on the emission spectrum. So again, you can see that over here. This is Bohr's model being able to explain the emission spectrum for hydrogen. And so that's why it was a very successful model. It could explain hydrogen atomic spectrum. It incorporated the quantization of energy into the model, which was classical physics. It was nice and easy to visualize as well, a nice easy thing to draw and visualize. And it explained why the electron wasn't really collapsing into the nucleus. But it wasn't 100% successful because people were still asking, well, why is it that electrons only exist here, here, and here? Why can't they really exist, maybe in between? Why is there no step in between there? Or why is there no step in between here? So it couldn't quite explain that. Bohr just said, there just isn't right now. And also, it couldn't really explain atomic spectra for more complicated things. It could explain the atomic spectrum for hydrogen, just no problem. But once you had more than one electron, then we couldn't really explain it. There were a lot of lines that couldn't be explained. So really, it was only good for explaining things that had one electron, like an ion with one electron, for example. But there were certain things like we'd predict one line, but for some reason there were 3 lines instead. You don't really need to know the Zeeman effect, but that's the idea there, that sometimes we'd expect one line, but there were 3 lines when we turn on this magnetic field. And why is that? Where is that coming from? And so Bohr couldn't explain stuff like that. So that's why Bohr's model didn't really work out very well. It's great for grade 11 and for certain courses where you need to simplify and just visualize nice and easily. But it doesn't really capture all the explanations we need. It can't explain all the spectral lines. So we need to modify our model further, and we're going to see that in the next lesson. So for this lesson, make sure you understand how Bohr's model came to be. I would recommend you try these practice problems here. We'll try them out in the video together, and then in the next video together. And just make sure you can explain the atomic spectrum using a Bohr diagram as well. So in the next video, we're going to see how we went from Bohr's model to the newest model, which is Schrodinger's model of the atom, with a few more contributions from other scientists.